Hello everyone. I'm glad to say hello to everyone after quite a long period when we didn't post in tutorials. We're gonna post more again. Today, as announced, we're gonna be covering this pattern and its development. First of all, it's been voted for by you guys. Thank you for expressing your opinion on our Instagram. We made a poll a couple of weeks ago. And basically this pattern is a little bit similar to the skewed quads from Lunchbox, but it's, I would say, a bit more intricate because it allows for variable strips width. And also it gives us an opportunity to skew it not in one direction, but actually in two directions. This skew can go in one way and this one can go in another way. Also, it allows us to create variable offset and variable thickness and so on and so forth. And I think this pattern can look quite interesting when you're working on some sci-fi buildings or sci-fi tilings and so on and so forth. Let's start.
Don't forget to check our parametric design market and available online courses on our website. Link in the description below.
Directly from here, I'm going to build a line SDL, which comes for start, direction, and length. We're going to construct point for start. For direction, I'm going to use X direction, which means this line will go to the right as we look at it. And for the length, I'm going to use something like 100. This is just some number. Doesn't need to be this. It can be pretty much anything. But as long as we are developing an abstract pattern, I think it can be just anything you feel comfortable with. And I'm going to extrude it to generate surface from that. Yeah, let's say this is going to be our base surface. And now, in order to generate these strips of variable width, I'm going to use the parameter subdivide surface component from Pufferfish plugin. Knowing the way that we constructed our pattern, our surface, right? We know that for U direction, we need to use just one division because we want our strips to be vertical. And for V direction, we need to use the component called careless range, right? Gonna set the number of strips as 16. Let's increase the errancy a little bit so we can get more variety, more variability in these strips. And also for the seed, I'm actually quite happy with the current one, but just for the sake of experiment, let's come up with something different. We can change the seed and we can get different results based on that. But to be honest, I'm quite happy with the default distribution like this. Now, what we need to do, we need to make sure we set up the direction for our panels, and therefore I want to use the isocurve component to extract U and V isocurves. And in order to get the sidemost edges, I will take the component that is called points. It's called numbers to points, I think. Numbers to points, yes, this one. I'm going to set the mask to XY, because this is a two-dimensional coordinate. And I'm gonna take the panel with numbers 0, 1, 1, 0. Multi-line data is gonna be deactivated. Sorry, not here, but here. And we connect it to UV. Right now and of course we need to graft this side, this part. And we have to reparameterize it. This way we're getting basically all the edges of these curves. And we will be interested in U isocurves, which are the longer ones in this case. But for us, what is important is not that they are longer, but the fact that they are going along our surface. Now, what we need to do, we need to divide them into certain amount of points, each set of these curves. And if we pay attention to the data structure of this tree, we see that the last two numbers in each path, they actually change from 0 to 1, 0, 1, 0, 1, and so on and so forth, right? What it tells us is that if we say shift paths, we can get those curves in pairs, and each pair basically belongs to one strip, right? What we have to do now, we have to divide those branches into two curves, curve number 0, curve number 1, and then we find the proximity between these curves, right? We take it like this. Proximity is basically the distance between closest points of two curves in a set, right? Something like this. I'm going to hide everything from before. And now I also want to go for careless range for the division. And I want to make sure that depending on how large is the distance between these 2 points, I want the number of divisions to be controlled by that. Let's take the remap, right? This one. I'm going to take the bounds, and we have to flatten the bounds so that this way we basically analyze the entire tree, not just a set, right? We take the smallest and the biggest of all the numbers in this data tree. And then we say construct domain. And actually I want to make sure that the wider this distance is, the fewer divisions there will be. Let's say I want to have at minimum 3 divisions, 3 points, and at max I want to have, 12, maybe 9, let's say. Let's go with 9 for now, and then we can increase it. And then we attach it here, and then of course we have to connect this curve and that and the other curve. We have to take the evaluate curve component, right? And we have to actually, let's do it like this. We actually have to connect these curves here. We also will have to graft them, in fact, right? We have to say, because we want each of these curves to get all those parameters. We also have to say duplicate data here, right, for these numbers. And because we wanted to have the same divisions, right, and we wanted these lines to be parallel. We don't want them to go just randomly, right? This line needs to be parallel to this line, at least for one strip, right? And here, what I want to do, I want to duplicate it twice, but then we have to say partition list, and we have to divide it into this number of elements. We say tree statistics. Actually, we can go for just list length, which will be faster. And then we connect it here. This is it. We connect it here, and you see immediately we're getting this pattern of points, right? And if we look carefully, we see that the neighboring strips actually have the same location of points, right? It's quite convenient, I would say. Also, one more thing to consider is that if we want this to look not like this it's quite random, but it still looks like a pattern, right? Especially here. If we want it to look a bit more random, we have to provide different seeds here. Let's go for random. I'm gonna go for 0 to 100 for the domain. For the number, I'm gonna need the amount of branches. Here we will have to use tree statistics. There is no other way to know. We have 16 branches, right? And then here for the seed, we can control it. We can make a slider from 0 to 100, just to control the seed of the randomness. And then we graft the result and we connect it here. We see now we're getting a bit more randomized distribution of points, right? Something like this will do for me, I think. All right. Also let's not forget to reparameterize these curves. I think they have already been reparameterized, but just in case, you never know, right? We are trying to make our script as modular as possible so we can attach different numbers to different curves to the file. And now what we need to do, we basically have to move each point up or down, depending on another random generator. But essentially what we want to do, we want to make sure that this angle is going to be the same for all the panels in our tree. In fact, we can also make sure that each strip, like each vertical strip, gets its own angle, but this is a bit deeper. We're going to concentrate on the basic scenario right now. the other scenarios can be made from what we're doing now. It should be also very achievable, right? How are we going to control this angle? Well, let's first of all, let's set something like 30 degrees angle. Let's turn it into radians, because we're going to be working with trigonometric functions, and it works with radians rather than with degrees. But for us, as for architects and designers, it's easier to understand degrees. Let's say 30, we convert it to radians, and then we need to find a tangent of that angle. And what is a tangent? Just to remind you, basically, if this is our panel, this angle can be 30 degrees. This is, let's say this is L, this is B. So B divided by L equals tangent of 30. Right? It's basically the length of the adjacent edge divided by the length of the opposite edge, right? For this angle. Not edge, but yeah, this like side of the triangle. Yeah, of course, this triangle has 90 degrees angle here. Having said that, we calculated this number, and then we need to move. So what it means for us practically, that we have to move this point, we have to move it up, for example, this point we have to move it down. And this distance is basically the proximity, this number between these two curves, right? I mean, I think it's pretty straightforward, but yeah, let me know what you think in the comments. Maybe you need a bit more, or maybe you would like to have a bit more explanation about maths. And also if you would like to have me making a tutorial about maths, trigonometry, or geometry in Grasshopper context, also please let me know. Because I think for me this topic is quite interesting, but let me know if you would like to know more. We know this distance, and as I said, if we move this point up and this point down, so we assume that this length needs to be divided by 2, right? Here we get another L, and this point goes up, and this point goes down. We have to divide it by 2. This length we divide it by 2. In a panel, we don't need a slider for that, right? We have 16 branches here, and we have 1 branch here, and here we have quite a lot of points, which is also fine. What we have to do, now we just need to work a bit with the data structure of our data tree. Let's multiply this tangent by the result of our division. And then we also have to multiply it either by -1 or by 1, right? You know what I would do actually? I would do the following, just to make our lives a bit easier. Because of course we can do everything in one data stream, but it's gonna be a bit less intuitive for us. What I'm gonna do, I'm gonna connect. No, forget about it. Let's do it in one stream. Actually, it's gonna be. I think it's gonna be. Is it gonna be easier though or not? No, I think we have to divide it. But anyway, we can do it at this step. We just say split tree, and we say tree statistics. Just to bring some more order into this script, and then we just say dispatch. That will do, right? Not this one, but dispatch. Is it dispatch? Yeah, this one. We dispatch the data paths of our data tree, right? Yeah, then we're basically moving those points. These points, we're going to be moving them up, these points down, or actually it's going to be quite random. Right, we have to multiply it by either by -1 or by 1. And what we're going to use in order to define if it's going to be 1 or -1, first of all, we create this panel with 1, -1, and we say we deactivate multi-line data. And then we use the component from Heteroptera plugin, which is called dice, this one, right? And here, for the number of values, we have to use the least length of those branches, right? And these branches, they basically, as long as we have 2 lines for each panel, for each strip, What it means basically is that this line and that line, they have to get the same numbers and same parameters, right? If this point goes up, this point has to go down, and vice versa, right? We can't, but by the same distance, we can't mess with it. And we physically can't, because we have equal number of points here and here. What it means is that we need to generate numbers for only one part of this tree, and then these points we will be moving up in this case, right? We'll be moving them by this number, and this part of the tree we're going to be moving them in the opposite direction, right? And how do we get this direction? Well, we need to take the tangent vector, right? Because apparently we're trying to use, like as always, we're trying to make our script as flexible as possible. Instead of just saying that, okay, in this particular case, we have a flat, vertically oriented surface. That's why we move the points up or down along vector z, I assume. We can say, you know what, actually, let's move it along the isocurves, because maybe, just thinking, maybe we have a surface which is not flat. Maybe we have a rule surface, right? In this case, it makes sense to move the points along the isocurve. Yeah, that's why we know this tangent vector, and we can actually use it. We can use the positive side of them. Let's say the amplitude, right? We take these vectors here. We take these values here, and we connect it to move. Right? You see how basically all these points are moved either up or down, right? This is actually quite. This is what I find quite interesting in Grasshopper. It's actually not B by L. It's L by B. I always get confused with this thing. So, all right. Apologies. Let's do it the other way around. Let's do it by division. Yeah, first of all, it's always good to check if the result looks credible. I mean, this movement, if it looks credible and fair. Second thing, another very important thing, when you're doing something very complicated or very high level, it's important to not forget the basics. Anyway, let's move on. We move these points up, and the other points, we will move them down, right? We move them by minus x. Here in expression, we say minus x. And there we go. And now, of course, we can just take the line component. No, actually not line. We need to say polyline, first of all. And we build our polylines here, right? We're getting the first polyline, and we're getting the second polyline, right? Yeah, these ones, right? It should be like that. You see, here we put the positive output, right? We move the first set of points, and here we move the second set of points, right? And you see this extension is it basically equals the extension to the other side. What does it mean for us? Well, actually it means that we have to say explode, right? And then just to check if we have done everything in the right way, we need to take the lines here. And it looks like everything's in order, right? Basically, this is how the pattern looks like. I think pretty cool. The only thing we need to consider is that, again, as I said before, if, let's say, our geometry is not so to speak. Okay, let's put it this way. We need to be careful if our surface is not flat, right? But for now, let me show you the principle on how are we gonna be building these things. You see, we get the lines, and basically now we need to build the rule surfaces between them to generate our panels. Again, very simple. Just let's do shift list here. We shift list by 1. Here we say invert. Here we should say minus x. which goes for -1, right? And here we also say invert. And now we basically build our ruled surfaces. This is our panels. And here you see this is a tricky moment, because here we start getting the self-intersecting surface, which is apparently not good. How can we fix that? Well, first of all, of course, we can drop this number a little bit, and this will solve the issue. Another thing we can do, we can always also increase this angle to make it a bit more. You see, if it gets to 90, these panels are gonna be flat, right? We need to, not flat, but like horizontal. We need to set this angle to the maximum of 90, and the minimum can be 30, let's say, just to make sure we don't get self-intersecting panels again. And you see, this is quite simple to change, right? And then we can also get a different scene. You see, we're getting different type of panels distribution. See, I personally prefer this one. Let me know in the comments what else would you like to cover about this type of geometry, and maybe which other pattern you would like me to cover next time. Now we need to get the profile of this panel. That's why we go for B-rep edges. We take the naked edges of those reps, we join them into single border, actually not a board, but like boundary curve. And now we need to go for an offset. We say offset curve. Actually, let's go for offset polyline. I think this one is going to be better. And again, assuming that this thing can be not flat, we can also find the exact plane of that curve, and we're going to use this plane for the offset. Something like this. And now for the distance, what we need to do, we need to take this, where is it? Here. We need to get this distance, right, that we used for the movement to the top, but this time we need to get this distance, right? We need to take the proximity divided by 2. And then we multiply this distance, the result, instead of just dividing it by 2, we have to multiply it by, let's say, 0.25 maybe, or maybe 0.5 to start with. Let's see what plays better. But also another thing to remember is that here we're getting many more of these curves, right? 93 to be precise. And we need to duplicate data. And we can't just duplicate it by some fixed number. We have to take the amount of panels in each of these strips. We go for list length. We take the number of strips here. We connected this part. And then we just need to say graph. We see we have 93 values, 93 numbers. We say graphed, and then we connect it here. And you see, this is the result we're getting. What we're interested in is the inner curve or the hole, right? This is it. You see, basically, no matter how narrow is this panel, it will always have an opening in the middle, which is quite handy for us, right? And here you see we can decrease this offset quite a lot. I'm quite happy with this result. And then what I'm going to do, I'm going to go for, by the way, yeah, we can also use not necessarily polyline offset, we can also use the offset curve loose if we're dealing with a non-flat, non-planar surface. But for now, we're going to be fine with that. We merge those curves with, also one important thing is to, actually this should match with this data. No, we have to say shift paths, because this component actually, the polyline offset, it always generates one extra 0 at the end of the path. And also one more important thing is that here we're getting a few different data structures, and we have to make sure that this one is respected. We need to make it principal, right? This data structures, we get data matching. And now you see we get 2 curves in each of these branches. And after that, of course, we can just say loft. And of course, before we do loft, we need to say align curve seams. Yeah, it's quite annoying, quite a long process, but I'm afraid it's the only one that we can do. To connect it here, we say snap, we invert it. Then we take list item, we take item 0, item 1. And then we flip this one following the other one, and then we say merge again. We merge them back, basically, right? Into one data tree. Okay, and now we're getting our geometry in order. This is it, right? What I would do after that, there are actually two ways. We can either go with a mesh, or we can also go with a B-rep. I would say I would go with a mesh. Let's just turn it into simple meshes. Of course, depending on what you need, if we need to get a filleted edge, maybe it's easier to go for B-rep. But for now, let's go for a mesh. Let's also say a weld mesh, just to be sure. And then we say mesh offset, and we offset it using variable distance, right? In order to achieve variable distance, we need to go for tree statistics. We take the random. We connect the count to the number of values. We say construct domain. And we need to set up some credible distance. Let's say we start at 5, more or less. Maybe this is too much, maybe with 2, and we add with something like 12. Let's see. Sorry, of course we need to graft it. I'm actually surprised it took so little time, because otherwise it would have crashed probably. Yeah, you see, basically we're getting this pattern in 3 dimensions, and then we have to. Yeah, we also have to turn it back into a polysurface if we want to. We don't have to, but I think it will give us a cleaner impression and render. We say mesh to polysurface, something like this. And then we go for custom preview. Of course, we need to set the color swatch. I'm gonna go for something like light gray, and yeah, let's look at it in rendered mode. See? Basically, this is our pattern. And we can look at it in. We can control the offset. We can also control the width of the offset. I think something like this will go. Yeah, this is it, guys. This is our pattern, which is 100% controllable, a pretty short script. Also can be very easily, very quickly manipulated and transformed. We can also, instead of using these numbers, we can use the graph mapper to control the distribution of divisions. And yeah, this is it. I hope you like this short and rather simple tutorial. Please let me know if what you think in the comments. Also, if you would like me to make any other tutorials, and any other, me or my colleagues will be happy to make it. If you'd like to support what we're doing, please check our website and check the parametric design market. We actually publish our scripts for patterns and any other tools there. And by purchasing them, you can support our free tutorials that we post for you. And yeah, thank you very much for your attention, and best of luck with your parametric designs. Bye.